Welcome to Physics Can Be Fun with me, Stephen Thomas. Today we're looking at the Doppler and our red-shifted universe. Now when we look out at the stars at night, we can see all these little suns, stars glowing out there. And scientists say that we can actually see all the stars in our own local galaxy called the Milky Way. And the furthest that the naked eye can see is about 1 or 2 or the maximum 4,000 light years away. So the wonderful thing about our universe is that it's like a time machine. The light that comes from the moon, for example, takes 1.3 seconds to get here. So we're seeing the moon as it was 1.3 seconds ago. If we look at our own sun, which we're not supposed to do, it hurts our eyes, it takes 8.3 minutes for the sun's light to get to us. So the sun could have gone out 8 minutes ago and we wouldn't even know it. The sun would still be shining brightly on Earth. And likewise, when we look at the stars, it's a time machine. We're seeing that star as it was when the light left there. And after the light left there, things could have happened on the star. And the star could be completely gone, and we'd still be seeing that star as it was when the light left there. So for example, our closest star, Alpha Centauri, takes 4 light years to get here. So at the incredible speed of light, it still takes 4 years for the light from our closest star, apart from our sun, to get here. And then, as I say, if we look further and further out, we can see the stars in our local galaxy, the Milky Way, and they take about, with the naked eye, you can see up to about 4,000 years ago. You can actually literally look into the past and see exactly how stars and things were 4,000 years ago. But if we now take our telescope and we now look into the sky, we can see into the past thousands and thousands and perhaps even millions of years away. So for example, if I looked at what looks like a little spot of light, a single star, through a telescope, I might actually be looking at the Andromeda galaxy, which is actually another hole like our Milky Way, full of thousands and millions of more stars. And then if you get the Hubble telescope, which is out there in space away from the haze of Earth, you can look back as far as 13.2, wait for it, billion years back. So with incredible telescopes like Hubble, one can see into the past. One can actually see the formation of the early universe less than 1 million years after the Big Bang, or God's act of creation, if you want to look at it like that. Science calls it the Big Bang, when apparently everything started from a tiny little pinprick and then spread out. And we can see early stars that were just formed fairly immediately after the Big Bang. And this is the amazing thing about cosmology. That's why these guys are so good. They can see literally into the past. But there's also, how do they know that the distance is this 13.2 billion years ago? Well, we know that the things we can see with our naked eye must be close. And there's certain things they call standard candle, stars that are a certain light intensity. And as you get a bigger telescope, you can still see standard candle stars that have the same intensity, but the further away they are, the fainter they are. So we need bigger telescopes, and obviously the biggest telescopes see furthest back. So by just the strength of our telescope and by comparing standard candles or stars that have the same brightness or luminosity, we can tell how far back we are looking, and science is pretty good at that. Now, stars also help us in another way, and that is they are composed of elements. The earliest stars were composed of hydrogen, which formed helium, and then lithium, and all the lighter elements up to iron. And then the star has to explode, and only then can the secondary stars start producing elements from iron onwards, the heavier elements. So the earlier stars were made out of the lighter elements, and the later stars were formed out of the heavier elements. And people know the process. It's nuclear fusion that joins the elements together. So from hydrogen we form helium, from helium we form lithium by just adding more and more protons, neutrons, and electrons together. But the interesting thing is that each element has got its own signature. So when you look at that star, light of a certain color reaches us, and we pass it through a prism. So here's our star, and the light comes and we pass it through a prism, and if it was white light, it forms violet, then indigo, then blue, green, yellow, orange, and red. So the light is spread into these various wavelengths, and violet is bent the most, and this is the highest wavelength. Now, if the star, for example, contains hydrogen, the element, it will produce, when we pass it through a prism, it will produce certain colors that are separated, and we call that the emission spectrum of hydrogen. And then helium will have its own emission spectrum that might look a little bit different. So these are the different wavelengths, from the highest frequency or shortest wavelength to the longest wavelength. And each element, hydrogen and helium, will have its own set of lines, almost like a barcode. So think of it, a barcode of different colors. You can tell exactly what elements there are in a star by looking at its emission spectrum. Now here is just something to show you. Let's see if we can get this working. I've got here some LEDs. They represent the different elements, and I can turn them on. Do you see how those LEDs are glowing? So there's a red, a green, and a yellow. Now what I have here is a potentiometer, and I can change the voltage. So if one were to look at our voltmeter, let's try and stand it up, you can tell the voltage at which each LED turns on. And what's interesting to note is that the red one will turn on first, then we get the yellow one, and then we finally get the green one turn on. And they don't all turn on at the same frequencies, at the same voltage. So our red comes on first, it's very hard to show, and then the yellow, and then the green. And there's a very good reason for that. I can't spend too much time on this, and we can actually tell the voltage at which these different LEDs come on. And let me tell you the reason for that. When you apply a voltage, you're giving energy to the alloys in each LED. And red, being your lowest energy, comes on first. Then you get your yellow LED come on, and finally you get your green LED come on. But you have to give the least voltage to get your red LED to come on. Your yellow takes a little bit more energy, and then your green will come on. And if you had a blue LED, it would take even more energy, and if you had a violet, it would take even more voltage energy. And you even get ultraviolet LEDs, which give off this lovely purple light, and they take the most voltage, something like 4 volts, to turn them on. So how does this relate to the signature of the different elements? Well, each element has got its own colors, its barcode, if you like, its emission spectrum. But now, this is the interesting thing where Doppler comes in. If you have these different frequencies, what we find is that normally with Doppler, if you have something moving, let's say we've got an aeroplane or a jet, There's our jet. And it's moving. It's giving off sound of a certain frequency. But when it's moving, what we tend to find is that instead of forming concentric circles, the frequencies tend to bunch up like this. The circles tend to, if this is the direction the plane is moving, we get a higher frequency on that side and a lower frequency. We spread the wavelength out on the side away from where the direction of motion. So towards the direction of motion, frequency increases. Away from the direction of motion, frequency decreases and increases on the direction towards motion. And the wavelength gets longer away from the direction of motion and gets shorter in the direction of motion. But this is the interesting thing about the universe, that if here is our emission spectrum for, let's say, hydrogen, all the frequencies from distant stars tend to be what we call redshifted. Their wavelength increases and their frequency becomes less. So all the colors of the rainbow get shifted downwards. So violet becomes indigo, indigo becomes blue, blue becomes green, green becomes yellow, yellow becomes orange, orange becomes red. Everything eventually in the universe, depending on how far you go, seems to be Doppler shifted, seems to have been stretched out. Now let's show you why this is. Here we have a wavelength in our early universe. Can you see how close those lines are together? That represents a high frequency, short wavelength. So here is our early universe, this balloon. Now we're going to try and show you what happened after the universe was formed. The universe began to expand. So I'm going to come here and show you our expanding universe. So as the universe expanded, notice what happens to the wavelength. The wavelength is getting longer and the frequency is getting shorter. It is getting redshifted, but notice that it's getting stretched out this way and stretched out this way if this is our star. It's getting, unlike a usual Doppler, which gets stretched on the one side and shrunk on the other, the universe seems to be stretching the wavelengths in all directions. So if our universe continues to expand, just look how stretched out that is. So the universe, as it's expanding, and space-time is expanding, all the wavelengths from the early universe are getting stretched out. We call that redshifted. And if we're sitting here, by the time the wavelength gets to us, the wavelength is very long or the frequency is very short. And so, due to our expanding universe and the length of time that it's been traveling, the longer it's traveled, the longer it's had, the longer it's been around in the universe, and it's had more time to expand. And so we find that the light from distant galaxies is very redshifted, or the wavelength is long and the frequency is short, and it's in all directions from every star in the universe seems to be redshifted. And that tells us that the whole universe, in fact time-space, seems to be stretching out. It's not so much that the stars are moving apart, it's that the stuff between the stars is moving apart, or is moving the stars apart. And we call that the redshift. And we can see that the older the universe, the more redshifted things are. So the closer things are to us, the sooner the light has left them, and so they're not very redshifted. And 13.2 billion years ago, things are very redshifted. So the redshift explains the age and the fact that the universe is expanding.